All right, so let's start. Let's take a sample of ice starting at -20 degrees, and we're going to keep the pressure at 1 atmosphere throughout this whole thing. We're not going to change the pressure. And we're going to assume that heat's evenly distributed. And what will happen if I start adding heat to ice at -20 degrees? And again, make sure that the heat is evenly distributed. I think it's impossible for us to do that. If you put like ice in a pan, it would not be heated evenly, and so the inside would not get heat at the same rate that the outside would. So it's a little hard to imagine, but just imagine that the heat's evenly distributed. So what's going to happen, and if you said it's going to melt, you would be wrong, because all that's going to happen is that the ice will warm up. So from -20 degrees to 0 degrees, as heat is added, the ice will warm up. It will get warmer, but it will stay a solid until it reaches the melting point. And again, it's hard to imagine, because if you tried to heat up them, you can't get the heat into the center as well. And so we're assuming that the heat gets evenly distributed all throughout. Anyway, from -20 to 0, the ice, it will stay ice, but the temperature will increase. Then what happens when you add heat and the ice is 0 degrees? Well, at 0 degrees, then the ice begins to melt. And the ice so you'll have some ice and you'll have some liquid. As long as there is both ice and liquid present, the temperature will stay constant at 0 degrees. So melting is endothermic, meaning we have to put heat in to melt the ice. So heat is added, but the temperature does not increase at all, because all of the energy at this point goes into breaking those molecular attractions. So it goes into, that's that heat of fusion. It's adding heat to break those attractions. So that will stay 0. So we'll stay at 0 degrees all through the melting process, and we'll have both solid and liquid present. All right, now once all of the ice has totally melted and we're at 0 degrees Celsius, if we keep adding heat at this point, now what we're going to do is we're going to increase the temperature of the water. So from 0 degrees up to 100 degrees, the water will remain a liquid, and the temperature of the water will rise up to the boiling point. So it will just keep increasing, increasing, increasing. At 100 degrees, the water will begin to boil. Again, we're always at 1 atmosphere, so that's why it's at 100 degrees. Now, throughout the process of boiling, because vaporization is also endothermic, we're adding heat. But even though we're adding heat, the temperature is not changing. The temperature will stay constant throughout the whole process, because all the heat is going to break intermolecular attractions until all of the liquid is vaporized. So that heat of vaporization is what's required to break those attractions. Once all the liquid has been vaporized, and now the gas is at 100 degrees Celsius, and if we keep heating up the gas, eventually the temperature should rise. I can't do it on this video. I can't show you these videos here on this video, because I'll get out of my PowerPoint. But if you want to go back, I have my PowerPoint on Canvas. You can go back and watch these. The simulation's kind of cool. You can change the temperature. The second one, PFET.Colorado, you can actually change the temperature and watch what's happening throughout the process. And this just kind of goes through what I just showed you. If we plot it, we get this idea. So you can see here we start at -20 degrees ice, and so we're adding heat at a constant rate. So this could be heat on the y-axis, or it could be time, because the heat's being added at the same amount per second. So anyway, at this point, all we have from some -20 up to 0 on this slope here, all we have is ice present, so solid. So this is the solid. Throughout the, when it's flat right here, maybe if I use a different color, so when it's flat right here, we have both solid and liquid present, because this happens to be water, but you're going to get the same pattern no matter what your compound is. So notice that when we have both ice and water in phase, both in equilibrium together, they're both there, that's at 0 degrees Celsius. That happens to be the freezing point or the melting point. This temperature stays constant. Then let's do purple. So once it goes from 0 degrees Celsius up to 100 degrees Celsius, here we only have liquid present while the temperature increases, and then while the water is evaporating, the temperature stays constant, 100 degrees. So we have both liquid and vapor present at the boiling point. And then once all of it's been converted to steam, and we again continue to increase the temperature, then the temperature will increase. If we keep adding heat, keep adding heat. Once it's all been evaporated, we keep adding heat and the temperature will keep increasing. So this is called a heating curve. This happens to be for water. If we have different compounds, then the basic shape will look the same, but you may have, if you're talking about the freezing point of alcohol, say, it might be a little higher than 0, and the boiling point might be a little lower, but it will still be flat at the melting point and the boiling point if you're going through all 3 phases. You can actually figure out how much heat is required for each phase of this diagram by using these different formulas at different points. So this is what we were just now talking about. So if we're talking about going from solid to liquid, 1 mole is the delta H of fusion. So so if you multiply the delta H of fusion times however moles of the liquid you have, or the ice you have, the solid you have to liquid, you'll find how much heat is required to melt your solid. And then just like we were talking about here, if you're trying to find out how much heat is required to vaporize from 1 mole from total liquid to vapor, you know the delta H of vaporization, and so that's per 1 mole, and you multiply by the number of moles, and you have the delta H for that segment. If you want to know how much energy it takes to melt ice, or to take ice from -20 and boil it up to 140 degrees, you're going to have to add each of these segments together. These formulas here are back from chapter 6. So if you want to know how much heat is required to go from -20 up to 0 as a solid, you need the mass of the solid in grams. You need the change in temperature, how much, because remember we use specific heat. This is specific heat. This is the specific heat specifically for the solid. So you take the specific heat, and that's always in grams per, it's in joules. Specific heat is generally given to you in joules per gram degrees Celsius. So you have to take the specific heat, multiply by the change in temperature, the total number of degrees Celsius, and then multiply by the mass in grams. And if you want to go back and look at, it might be chapter 5, it might be chapter 5 or 6, heats of reaction. Okay, and same thing here. This is a specific heat for the liquid, multiplied by delta T times the mass. And here would be the specific heat for a gas, times the delta T times the mass. So you have to do, so if you want to know how much temperature, how much energy is required to go from -20 up to, say, 60, you have to do the segment here where you're heating up the ice, you have to do the segment where you're melting the ice, and then you have to do the segment where you're heating up the water. So So you figure out where you're starting, where you're ending, and if there's a phase change in the middle, you have to add that to it. I think I have an example on the next slide. Yeah, so the heat of vaporization for ammonia, now this is just actually, this is just that segment. So in this case, what we're doing is we're vaporizing 1 kilogram of ammonia, and all they're doing is they don't even give you the boiling point. So in this case, all they want to know is how much energy is going to be required to vaporize 1 kilogram of ammonia if the delta H of vaporization for ammonia is 23.4 kilojoules per mole. So kilojoules per mole, we know how many kilograms we have, so somehow we have to convert kilograms to moles. If you go back and look at it, the delta H for this vaporization will be, well, it's for the transition, for this transition. It's going to be the number of moles times the delta H of vaporization, because the delta H of vaporization is per mole. So we need to take the delta H of vaporization, which is this number, multiply it by the number of moles that we have, and that's the delta H for this process. So what we have to do is figure out how many moles 1 kilogram is. So 1 kilogram, which is 1,000 grams, a molecular weight of NH3 is 17, so 1,000 divided by 17 gives me 50. So I have 58.8 moles of NH3. So now I just take 58.8 multiplied by delta H per mole. So 58.8 times the delta H of vaporization per mole gives me the 3 significant figures. 1.38 times 10 to the 3, or 1,380 kilojoules is required to vaporize 1 kilogram of ammonia. In a second example, now I'm kind of going back to that, thinking through this process. So how much heat is required to convert 12 grams of ice at -5 degrees Celsius to liquid water at 1 degree Celsius? So keep this in mind. I'm going to draw my little scale here. So we're going from -5. First, we have to raise the temperature of ice from -5 to 0. Then we have to convert it to a liquid, so we're going from 0, so we're going here, so we're going from solid to liquid, so that we need the delta H of vaporization for that. And then we're converting going from 0 degrees up to 1 degree Celsius. And so we have to figure out all 3 of these segments and then add them together, and that's how much heat. So we need to find out how much heat is required to raise the temperature of ice from -5 to 0. Then we need to know how much heat is required, or how much energy is required to melt all of that ice. And then we need to know how much is required to increase the temperature of the water from 0 to 1 degree. So we're going to have to use all 3 equations. So let's just figure, so for the first segment, which is right here, a different color, we need S equals heat. That was the equation on the last slide. Q, heat, equals SM delta T. So we know our delta T is 5 degrees, because final is 0 minus initial -5. So delta T is 0 minus a -5, or 5 degrees. M is the mass, and it's 12 grams. And we need the specific heat of ice, which is right here. Specific heat of the solid is 2.09 joules per gram degree Celsius. Let me see what I have here on my, so yeah, we need to look at 3 parts of the graph. So from -5 to 0, we're using delta H equals mass, 12 grams, times delta T times S solid. And I just kind of pulled that out. I think on the next slide I work through the process. Then we need to find the amount of energy needed to melt the ice. So that is how many moles of ice we have times the delta H of fusion, and the delta, I think I'm missing my delta here. The delta H of fusion is 6.02. And then, like I said, we need to have this, the delta H equals SM delta T, but this time we need to have the S of the liquid. And this is just given to you so that you know the melting point. You know, if this wasn't water, I assume you know the melting point of water is 0, but if this happened to be ammonia or something else, you would need to know what the melting point is to see if you're going through a phase change from your initial temperature to final temperature, which we are. And then finally, so we have to heat the water from 0 degrees to 1. So we need the mass again, which the 12 grams, times the delta ET, in this case is just 1 degree, times the S of the liquid, which is given to us. So let's work through each of those parts. What I first did is I converted 12 grams to moles, because at one point we need moles. Sometimes we need grams, sometimes we need moles. So to heat the solid from -5 to 0, we have 12 grams of ice times delta T, which is 5 degrees, times the specific heat of ice. So that's 125.4 joules. Now you'll see why I converted it to kilojoules in a minute, but you could just leave it at joules if you want to for now. So that's how many joules of heat there is to heat the ice from -5 to 0. To melt the ice, this time we need moles times delta H of fusion, which is 6.02. So notice that in this, so notice here the grams cancel, up here grams cancel, degrees Celsius cancel, so my answer's in joules. Here moles cancel, and so notice that my answer's in kilojoules, that's why. So 4.02 kilojoules. And then finally, heating the liquid from 0 to 1, we need the 12 grams, that shouldn't be there. We need the 12 grams times 1 degree Celsius, which is the delta T, times the specific heat of water. So again, grams will cancel, delta C, or change it, the temperature, and so my answer is in joules. Now, because we have to add these up together, I converted everything to kilojoules. So 50.5 joules is 0.0505 kilojoules. So the total amount of heat required is 0.125 kilojoules plus 4.02 kilojoules plus 0.0505, or 4.20 kilojoules. You can see most of the energy is coming from the melting the ice, but there is some energy needed to raise the temperature of either the water or the ice. So that's the kind of process you're going to go through. Okay, we're going to switch topics, and we're going to talk about phase diagrams. So a phase diagram is a little bit different, and it's a graphical way to summarize whether you are a solid, a liquid, or a gas. And actually sometimes there's different types of solids, so we'll see that in a minute. And we're going to see what conditions they are under certain particular temperatures and pressures. So we're able to predict the phase of a substance at any given temperature and pressure. So as you'll see on the next slide, the diagram is divided into areas which represent each state of the substance. And like I said, most of the time it's just solid, liquid, and gas, but sometimes there's sometimes different types of solids that we'll see. And then the curves separating each area represent the boundaries, and so that is where the phase change occurs. So let's look at that. It's easier to see. All right, so you can see here, this is a typical phase diagram for a single substance. So you can see that we've got temperature on, I'm going to use a different color. We've got temperature on the x-axis, and it doesn't matter what the temperature is in, whatever unit you want, and pressure. And same thing, pressure doesn't, usually we'll use atmospheres, but you can use whatever pressure unit you want. Notice that we have our three different regions, solid, liquid, and gas, and it should make sense that at higher temperatures, we're going from solid, liquid, gas. Pressure, gas at low pressures tends to be gas, but you know, there's little things going on here. So let's kind of look at each of these in order. So this line between A and B, and this dot should really be like right there, so it's kind of hard to see. Okay, so this line AB is the boundary between solid and liquid. So that would mean if I anywhere on this line, I am at the melting point. So depending on what the pressure is and the temperature, that's the particular melting point. At a higher pressure, the temperature is a little bit lower. But notice that it's pretty steep, and so we know that pressure doesn't change melting point too much. It does change it a little bit, but not that much. So it's usually a steep curve there. So anyway, if I'm on this line, I have both solid and liquid present, and that will represent the melting point at that particular pressure and temperature. Kind of an interesting thing, if the line is, the line goes to the left, what that means is the liquid is more dense than the solid. And that's an unusual case, which happens with not many liquids, but it does happen with water, and we'll talk in a little while about that. But so what happens is that the melting point decreases with pressure, which seems a little unusual, and that indicates that the liquid is more dense than the solid. So if the line kind of veers to the right a little bit, or is then this means that the liquid is less dense than the solid, which is kind of more normal for most liquids. So that last one was probably water, and this is probably like alcohol or something a little bit different. Okay, now the curve AC represents the boiling points of the liquid at different pressures. And you can see that it definitely changes a whole lot more with pressure. Temperature and pressure change a whole lot more, so that line is kind of more spread out. But if you're on the line, you've got both liquid and vapor present. If you're to the right of the line, it's vapor. If you're to the left of the line, it's liquid. And then down here between, so A and D, you've got your equilibrium between a solid and a gas. And so again, on the line, you've got both solid and vapor present. If you're to the right, it's vapor. To the left is solid. The triple point, which is point A here, is the point. It's the temperature and pressure where all three phases of a substance exist at equilibrium. So, so at this particular temperature and this particular pressure, you're going to have all three phases present at the same time. Here is a phase diagram for water. So you can see that the line here kind of goes up to the left a little bit. This is not to scale, so just notice that. But here, so interesting to note that if you've got at 1 atmosphere pressure, right, that's our normal, here's our normal freezing point, which is 0 degrees Celsius. And at 1 atmosphere pressure, it runs into the vapor line at 100 degrees. So you can see that at 1 atmosphere pressure is liquid between 0 degrees and 100 degrees Celsius. They're telling you what the triple point is. The triple point of water is actually at 0.01 degrees Celsius and at 0.00603. So you have to have very low pressure to have solid, liquid, and vapor all present. But it's right close to the freezing point of water, but you have to have very low pressure. So if I'm at a higher pressure, and you can sort of see what we were talking about at higher pressures, you can actually, the freezing point goes down just slightly, very slightly, but the boiling point, let's say we're at, 2 atmospheres pressure, like in a pressure cooker. So you can see here that the boiling point is much higher. So, and if you're at a lower pressure, the boiling point is lower. So you can kind of see that. This, which we'll see on the next slide, is called the critical point. It's the highest point where liquid is present. And so anything above that temperature and pressure is only vapor phase. And it happens to, the critical point for water happens to be at 374 degrees Celsius and 218 atmospheres. Here's showing you just a couple of things. So the one on the left here is carbon dioxide. And what I particularly want you to see, so notice where the triple point is, negative 57 degrees Celsius and 5.1 atmospheres. That means liquid is cannot exist at lower pressures than 5 atmospheres. And that's why we have dry ice. So at normal pressures, 1 atmosphere pressure, you can see that we go straight from a solid to a liquid. So this point is the sublimation point, and this is why dry ice is so cold, because dry ice it melts at negative 78 degrees. So if you've got dry ice, don't touch it with your fingers because it's negative 78 degrees Celsius. You might say, wait a minute, when I see dry ice, I see droplets of liquid. That is not the CO2. Those droplets of liquid are actually water vapor from the atmosphere that because it's so cold, the water droplets in the vapor are actually being condensed to liquid. And so if you see liquid that's next to dry ice, it's because it's actually condensing the water vapor into a liquid, and so that's what you see. Anyway, so that's why CO2, dry ice, it does not go through a liquid phase at all. It sublimates. The only way that you could get liquid CO2 is to raise the pressure quite a bit. So if you're above 5 atmospheres pressure, you can have liquid CO2. This picture over here is actually sulfur. And again, none of these are to scale, but this is what I was talking about before, that you can see that there's actually a fourth region. And that is that at some pressures and temperatures, we have this rhombic shape solid. And at some temperatures and pressures, we have this monoclinic, which is a different, you can see it's a different shape to the solid. And so this is just showing you if you have more than one different solid, you may get a slightly different phase diagram, but you get the whole idea that here, if you're at this point, pressure and temperature, then you're at the phase between rhombic and the gas. If you're at this temperature and pressure, you're going to be at the point where the rhombic changes to monoclinic. Of course, if you're right in the center here, then at that point you're monoclinic or liquid here. There's 2 triple points. There's a triple point for the liquid monoclinic and gas, and then there's triple point. Oh, there's 3 triple points. One between the rhombic monoclinic and gas, and then up here you've got the triple point between the rhombic liquid and monoclinic. Anyway, you get the idea. We're not going to get too complicated, but I just wanted to show you that there are some other phase diagrams. And so, like I said, the very final point, the C is the critical temperature. This is the point, the temperature above which the liquid no longer exists, regardless of the pressure. And so we only have gas above the critical temperature. So here's an example. My lines aren't perfectly lined up, but you get the idea. Shown here is a phase diagram for compound X. The triple point of X is at negative 25.1 degrees Celsius and 0.5 atmospheres. So I've kind of lined up those pressure and temperature. And the critical point is at 22 degrees Celsius and 21.3 atmospheres. So here's some questions. What is the state of X at position A? So A is like right here. at that point? Well, you should be able to see that that's a gas, right? So the state is a gas at point A. If I start at point A and I decrease the temperature to negative 28.2 while holding pressure constant, what will the state of X be? All right, so if I start here and I decrease the temperature and I'm going to negative 28, so I can see that negative 28 is less than the triple point. So here, negative 28, somewhere around here. So I'm holding the that's supposed to be a straight line. So if I go a straight line holding pressure constant and I decrease to negative 28, it should be now, here's my gas and my liquid and my solid. So now it should be a solid. So the state of X at question B, it should be a solid. All right, if we take the compound starting under the conditions of part B, so if we're at this point here, and we increase the temperature back to 15.3 degrees, so now we're obviously somewhere in here, because I don't know exactly what the boiling point is, but you can sort of see if 20, 22, and 25 is probably, we're somewhere around here, I think. And we decrease the pressure, so it's not critical. We decrease the pressure to 0.002 atmosphere, so we're way down here. What phase will we be in? And you can clearly see you're in a gas. I should use a different color here. Let's do that. So if we increase to 15.3 and then decrease. And then question D, would it be possible to make the compound starting under the conditions of part C, so we're down here, would it be possible to a solid by increasing just the pressure? Maybe. This one's a hard question, so let's go with green here. So if we start here and we just increase the pressure, will we eventually get a solid? Possibly. If we go to a higher temperature, we never will, but I suppose if we run into this, if this line just keeps going and going, we may run into that line, so it's possible.